So in the last video, we took a look more at the normal force and friction. And here I want to spend some time on drag and maybe do a few more examples with Newton's laws of motion. So drag is force of air resistance. It always opposes the motion. So it means it's anti-parallel. Remember, that just means points in exactly the opposite direction of the velocity. So there's a couple different models of drag out there depending on the kind of fluid that you're going through. Are we talking air? Are we talking water? And the shapes of objects and stuff like that. But the one that applies for most situations that we care about is that the magnitude of the drag force is 1/2 CD rho AV squared. And again, this is not a rho, a P, this is a rho. So again, with the special paper that we all used, you draw it like that. And this is what's called the coefficient of drag, or the drag coefficient. This is going to depend on the materials that the surface is made out of, and also the general shape. Does it have like a, if it has a more aerodynamic shape, the coefficient drag will be lower. If it's a boxier shape, it'll be higher. This rho here is the density of the fluid, usually air. And this A here is the cross-sectional area. So in other words, how much space would it take up in a photograph if you're going to look at it as it's flying head-on toward you? So for instance, if you're looking at a skydiver, before they pull the parachute here, their cross-sectional area would be kind of small. But then after they pull the parachute, now their cross-sectional area just got a lot bigger. And then V is the speed of the object. Now, for most typical, if you just want a really rough number, to, you don't want to think about it too hard, you can say that for a lot of typical objects going through air, as long as you're not at crazy altitudes or anything like that, you can usually roll in the coefficient drag, the density of the air into the magic number 1/4 kilogram per cubic meter. So if you're just looking to ballpark a number, that's just a quick and dirty way to do it. Otherwise, coefficients of drag usually have to be either determined through very careful computational fluid dynamics considerations or experimentally obtained in a wind tunnel. So because the drag force depends on the velocity, it turns out that trying to incorporate it into Newton's laws of motion gets absolutely horrendous. And if you're to try to roll this in with kinematics or anything like that, since the drag changes with velocity, that means the acceleration of the thing is going to change with velocity, and that is way beyond the scope of this course to be able to handle. So is there anything we can say? And it's like, sure, we can find what's called the terminal velocity of something. So this is if the only two forces acting are gravity and drag. At some point, the usual situations, like say a skydiver jumps out of a perfectly good airplane or something like that, at first you'll have a big force of gravity and a small force of drag, and so then that means F net will point down, so the acceleration will go down. Well, as you pick up speed, this drag force will keep getting ever bigger and bigger until eventually it's the same size. Now, this can work the other way too. If something is like, if you fire something out of a cannon or something like that, you could be going so fast that the drag force is greater than the force of gravity, in which case the acceleration will be up, and as you lose speed, you'll eventually get to a point where the gravity and drag are equal. In either case here, at the magic speed where this happens, we call this speed the terminal velocity. It should really be called terminal speed, but the physicists aren't always super consistent with their names of things, unfortunately. So at this terminal velocity, the drag force and gravity are equal. So in that case there, we can go ahead and equate the two forces and say that drag will equal gravity. And so we can go ahead and put in our 1/2 CD rho AV squared. Gravity will be equal to mg. And so we get that V will be equal to 2 mg over CD rho A. Take the square root. So what we get out of it is that for the same cross-sectional area, if something is more massive, so this will generally correspond to the object itself being more dense, the terminal velocity will be higher. So this means that we can neglect air resistance for longer before we have to start worrying about it for that object versus one where the density is lower. You can convince yourself of this by, say, taking a piece of paper, wadding it up loosely, throwing it as hard as you can. That will make the cross-sectional area nice and big. It won't go very far. Then if you wad it up as tight as you can, that makes the cross-sectional area real small. Throw it just as hard, you'll probably find the sucker flying across the room. So anyway, that's about all we can access in the case of drag here. I had debated about presenting elasticity in this series, but I decided against it because you're not really going to need it for anything going forward after this. So I'll instead finish this out with doing one more example, sort of reminiscent of Atwood's machine, just to give us some idea of how to tie together a lot of the things we've been doing. So here, let's say we've got a tabletop surface. There's a massless frictionless pulley here. Let's say I've got myself a 2 kilogram block here. I'll call it M2 just because otherwise I'm going to get really confused because I'm going to put a 1 kilogram block here, so I'm going to call that one M1. And we just connect them with a string over the pulley. And we'll say that the coefficient of kinetic friction between the surfaces here is 0.2. So this will be moving to the right, this will be moving down, and in fact their accelerations will be right and down as well, and we're going to assume the string doesn't stretch. So that means that the A's will be equal in magnitude. So what I'd like to know is just plain, what is the acceleration equal to here? And spoiler alert, it's not 9.8, in case you were thinking it was. And remember, this is because g is not an acceleration. So we can tackle this in the spirit of Atwood, but we're going to have to keep in mind now that M2 is also going to have a force of kinetic friction acting on it, so that means we're going to have to work a little harder. So let's start with the easier object. We'll look at this guy right here. The contact force acting on it is tension, and then there's also a force of gravity, Fg1. So we can go ahead and write Newton's second law of motion for it. So free body diagram down, Fg1 down, tension up. We're probably going to be best off choosing down to be positive to match the acceleration. So then, just like before, this is going to give us Fg1 minus T equals M1A. All right, now let's go ahead and look over here. So I do this free body diagram. I'm going to have the normal force up. I'm going to have Fg2 down. I'm going to have tension to the right, and I'm going to have kinetic friction to the left. Now these tensions are a pair of forces that act as if they are an action-reaction pair. So let's first start in the land of y. We'll have that the normal force minus Fg2 equals ma sub y. And since it's neither levitating off of or crashing through the table, a sub y is 0. So we get that the normal force is equal to Fg2 is equal to m2g. All right, in the land of x, we'll have the tension acting to the right, kinetic friction acting to the left. That has to equal m2a. All right, from our model of kinetic friction, this will be T minus mu kn equals m2a. We just worked out that the normal force is m2g. So this is T minus m2g equals m2a. Now we can do the same trick we did before of adding these equations to make the tensions go away, so let's do that. If I were to follow this one through for just one more hot second, this would be m1g minus t equals m1a. So let's add to this equation m1g, oops, dropped my mu k right there, m1g minus t equals m1a. So adding the two equations, the t's will cancel. I'll be left with m1g minus mu k m2g equals m1 plus m2a. So my acceleration will be, I can pull a g out from here, m1 minus mu k m2 over m1 plus m2g. Sticking in our numbers here, this will be m1, we said it was 1 kilogram, minus 0.2 times 2 kilograms over 1 kilogram plus 2 kilograms times 9.8 newtons per kilogram, which we will rewrite as meters per second squared since we're solving for an acceleration. So that will yield 1.96 meters per second squared. And I will close this particular one out by just throwing in a little trick. I didn't really know where else to put this, so I'll just talk for a quick moment about cleverly choosing free bodies. Now, you may not have realized this, but whenever we choose a free body, unless we're looking at a single atom, we're always looking at a collection of atoms. There are always interatomic forces happening, and we never worry about them. Later in the class, we'll prove why we never worry about them, but for now, as long as forces are internal to a system, we don't worry about them. And this extends even to the macroscopic. So let's say if you have some sort of a problem, like let's say you've got a bunch of boxes tied together by ropes and you're giving them a tug. The obvious choice, and let's say you want to find what the acceleration is, and you want to find what the tensions are between the strings. The obvious choice would be to make this a free body, that a free body, that a free body. And that will absolutely work, but the math will be complicated. A less obvious choice would be to make this a free body, this a free body, and that a free body. So whenever I draw a circle around it, that makes all the forces internal. So I draw this bigger circle around M1 and M2. This tension is an internal force, which, like I say later, we'll prove we don't care about. But what that means then is that the only force in the x direction acting on on this free body is just T2. So if we've already solved for the acceleration, then just boom, out pops T2, and the math is a lot easier. Just a little something to have in your back pocket. All right, I will catch you in the next videos. Catch you all later in cyberspace.